There's a rule in our universe that we're told is unbreakable. A cosmic speed limit set at roughly 300,000 kilometers or 186,000 miles every single second. It's the speed of light. From our very first science class, we learned that nothing, no object, no information, no starship can go faster. But what if that's not the whole story? What if I told you there's a massive loophole in that ironclad rule, that the fastest thing in the universe isn't a thing at all? What if the very fabric of space is stretching so fast that it's outrunning light, rewriting our entire picture of the cosmos in a way that's perfectly legal under the laws of physics? To get how the universe pulls this off, we first need to understand why the speed of light is such a tough barrier. This isn't some random number someone made up, it's a core piece of Albert Einstein's theory of special relativity. His theory connects space and time into one thing, space-time, and it shows us something incredible about mass and energy. You know the famous equation E=mc². It tells us that mass and energy are basically two sides of the same coin. An object just sitting there has a certain amount of energy locked away in its mass. But if you want to get it moving, you have to pump in more energy. Kinetic energy. Here's the catch. As an object with mass gets closer and closer to the speed of light, the amount of energy you need to push it just a tiny bit faster skyrockets. Think of it like pushing a car. At first it's hard, but you get it rolling. Now imagine that the faster the car goes, the heavier it gets. As you approach the speed of light, its effective mass blows up, heading toward infinity. To actually hit that ultimate speed would take an infinite amount of energy, which is more than the entire universe has to offer. This speed limit applies to everything with mass, from protons to planets, and it even applies to information itself. That's why you can't just send a radio message to a distant star and have it get there faster than light. It's the law. But what if you didn't have to move through space to get from one place to another? This is the secret, the loophole that changes everything. The speed of light is a limit for objects moving within space-time. It says absolutely nothing about the expansion of space-time itself. The universe found a cheat code. Instead of moving the players on the board, it just decided to stretch the entire game board. The classic analogy here is a balloon, and for good reason. Imagine you draw a bunch of dots on a deflated balloon. Each dot is a galaxy. Now start blowing up the balloon. From the point of view of any one dot, all the other dots are moving away, but here's the key part. The dots aren't actually scurrying across the rubber. They're staying put on that patch of the surface, but the rubber itself is stretching, carrying them apart. A dot 1 inch away moves away at a certain speed, but a dot on the far side of the balloon, maybe 3 or 4 inches away, seems to move away much faster because there's simply more expanding rubber between them. Our universe works the exact same way. Galaxies aren't spaceships blasting through the cosmos. For the most part, they're just chilling in their local patch of space. But space itself is expanding everywhere all at once. And just like with the balloon, the more space there is between two galaxies, the faster they appear to drift apart. This isn't motion through space, it's the expansion of space. And that expansion has no speed limit. This wild idea isn't just a theory, it's one of the most solid facts in all of cosmology. And for that, we can thank the astronomer Edwin Hubble. Back in the 1920s, Hubble was looking at distant galaxies and noticed something strange. The light from nearly all of them was redder than it was supposed to be. This is a phenomenon called redshift. It's like the Doppler effect you hear with a siren, where the pitch gets lower as it moves away from you. Light does something similar. When an object is moving away from us, the light waves it emits get stretched out, shifting them toward the red end of the spectrum. Hubble found that almost every galaxy he could see was redshifted. They were all moving away from us, but then he found something even bigger. The farther away a galaxy was, the more its light was redshifted, which meant it was moving away faster. This perfect connection is now known as Hubble's Law. It was the first real evidence that our universe wasn't some static, unchanging theater, but a dynamic, expanding cosmos. Today we know this redshift isn't just a simple Doppler effect. It's the light waves themselves getting stretched by the expansion of space on their long trip to our telescopes. Scientists measure this expansion with the Hubble constant. It tells us how fast space is expanding for a given amount of distance. The current measurements put it around 70 kilometers per second per megaparsec. A megaparsec is just a giant unit of distance equal to about 3.26 million light years. So for every 3.26 million light years you go out, a galaxy is moving away from us another 70 kilometers per second faster. That might not sound like much, but across cosmic distances, those speeds really add up. And eventually, they break the light barrier. And this is where it gets really weird. If you do the math with the Hubble constant, you find that once you get out to a certain distance, around 14.4 billion light-years, the combined stretch of space between us and a galaxy that far away means it's receding from us faster than the speed of light. This boundary is called the Hubble Sphere. Every galaxy beyond it is currently being carried away from us superluminally. So the obvious question is, if a galaxy is moving away faster than light, how on earth can we see it? Shouldn't its light be like someone trying to run up a down escalator that's moving too fast? The answer is one of those beautiful aha moments in science. The light we see from that galaxy today didn't start its trip today, it started billions of years ago. Back then, that galaxy was much closer to us. It was well inside our Hubble sphere, where the expansion was slower than light speed, so that little photon of light began its journey, traveling through an expanding space. It was like a swimmer in a river where the current is constantly speeding up. For a while, the current might have pushed it backward relative to us, but it kept swimming through its local patch of water. Eventually, it crossed into a region where space wasn't expanding away so fast, and finally completed its long journey to our telescopes. This is why our observable universe, everything whose light has had time to reach us, is much bigger than 13.8 billion light-years across, even though that's the age of the universe. The true distance to the edge of what we can see is about 46 billion light-years. But because the expansion is accelerating, there's another more permanent boundary called the cosmic event horizon. Any galaxy that crosses that line, currently about 18 billion light-years away, is lost to us forever. We can see the light from its past, but its future light will never reach us. This is all pretty confusing, so let's clear up a couple of common mistakes. Myth 1. The Big Bang was an explosion at one point in space. We think of an explosion as something happening in space, like a bomb. But the Big Bang wasn't an explosion in space, it was the start of the expansion of space itself. It happened everywhere, all at once. The raisin bread analogy works perfectly here. As the dough for the bread rises, it expands everywhere and carries all the raisins apart from each other. There isn't a center of the explosion inside the bread. The rising is happening throughout the whole loaf. Our universe is the loaf. Myth 2. The expansion of the universe breaks the laws of physics. Actually, it's the opposite. The expansion is a direct prediction of Einstein's theory of general relativity. When he applied his equations to the whole universe, they showed that it had to be either expanding or contracting. He thought that couldn't be right, so he added a cosmological constant just to force his model to be static. When Hubble proved the universe was in fact expanding, Einstein famously called that fudge factor his biggest blunder. The same theory that sets the speed limit for travel through space is the one that says space itself can expand. So not only is the universe expanding, but as astronomers discovered in 1998, that expansion is speeding up. For the first several billion years, gravity from all the matter in the universe was acting like a brake on the expansion. But about 5 or 6 billion years ago, something else took over and slammed on the accelerator. Scientists call this mysterious force dark energy. We have no idea what it is, but it acts like a kind of anti-gravity, a pressure baked into space itself that pushes everything apart. It seems to be a fundamental property of the universe, and it makes up about 70% of everything in it. This is the stuff that's driving the runaway expansion, pushing more and more galaxies over our cosmic horizon and making sure that the fastest thing in the universe is, and will continue to be, space itself. The universe is so much stranger and more incredible than we can imagine from our little corner of it. The speed of light is a very real, very solid rule for anything moving within the cosmos. But the cosmos itself doesn't have to follow that rule. The expansion of space-time is something else entirely. It's not about traveling between 2 points, but about the very distance between those 2 points getting larger. It's a cosmic loophole that allows the universe to create distance faster than light can cross it. So the next time you look up at the stars, remember you're staring out across an ocean of expanding space, where the most distant shores are already moving away from us faster than light, carried off on the stretching fabric of the universe. If this deep dive into cosmic rules or loopholes blew your mind, please give this video a thumbs up and subscribe for more journeys into the biggest questions in science. And let me know in the comments, what other cosmic mystery are you curious about? Thanks for watching.